Share with us, and let's try to focus on addressing the needs of the others. All right. Can I begin now? So we have different types of loading. So these are the very common modes of loading, simple loading. We have axial tension. There you go. So axial tension, wherein you have the bar being loaded along its longitudinal direction. You have bending. So our focus will be at the moment bending, wherein you have the load to be perpendicular to that of the longitudinal direction of this beam. So if a specimen is loaded along its axial direction without any effects of bending, we simply call this one as a bar. If you have this specimen loaded along its transverse such that it will be deforming based on bending, so you will have a beam here. So we have here twisting, wherein you twist a certain object and you have this axial load. Buckling, wherein you have a very long specimen loaded along its longitudinal direction. Now, we'll be discussing this one as we go on, but at the moment, these are the common modes of loading. Axial tension, bending, twisting, and buckling. Okay, so this one is still in modal. It's not in finite element, but this one is in modal. Okay, so don't worry about this one, you can download it later, but it has been there since. Okay, beams loaded along its transverse direction. Okay, so for simply supported, we have this one to be pinned. What do you mean by simply supported? Simply supported is simply supported. If you have this one as your beam, okay, a simply supported is just being placed on top of a support. Okay, meaning that it can move freely. So it can slide, but so it can slide here, but it cannot move along its support, along the transverse direction. But normally what we do is we have this one here, where one is pinned, and then we have this one to be a roller. Meaning that this one can slide here, okay, something that's fixed here, and it can slide somewhere here. So this is how we represent a simply supported beam. Simply supported. There will also be a cases wherein one end is fixed and the other is free. So we're going to discuss that later. We have now here the different types of loading for beams. Very simple, concentrated load or distributed load. Okay, concentrated meaning just one load at one point, while distributed load can be load which will be along a certain length or span of a beam. Okay, so this is the length, that will be your axis. Load will always be along the transverse axis. Transverse axis meaning perpendicular to that longitudinal axis. Longitudinal meaning this one here along the length. Transverse perpendicular to that longitudinal axis. So this is now your types of support. We have different beams, definition based on the types of support. So here we have here a simply supported beam. So here we will have just reaction forces at the ends. What do you mean by reaction forces? Some forces that tries to balance the beam so that it will be at static equilibrium. Okay, reaction forces. Reaction forces will be at the supports. Okay, or boundary conditions. So in finite element, we've been talking about boundary conditions. So in boundary conditions, there will always be some reaction forces or reaction moment. Now, so last time we discussed about a simple problem. So we had a simply supported beam. For a simply supported or simply support, there won't be any moment, just transverse forces at the supports or transverse reaction forces at the supports. Please take note when I mention reaction forces, these are just the balancing forces. Okay, when I mean loads, so these are the actual loads that you apply. So we'll talk about that with some examples. So here we have a fixed support. You will have a moment. So as you can see, this is simply supported. This one is fixed. There will be a moment and a reaction force. Okay? So at the end, what will be our boundary conditions? This one is free, by the way, so we will see later. So just take note, for a simply support, you just have a reaction force. But for a fix, you will have a reaction moment and a reaction force. So as you can see, that's fixed. Now, we will be also determining some, or we will be using other parameters such as theta or your slope. Okay, so that's the angle. When this one bends, there will be that certain angle. Okay, which we can define the bending of the beam. Of course, there will always be that deflection U2 because we're using U1 along X and U2 along the Y axis. Okay, so these are the boundary conditions again. Okay, so please take note. At simply support, the deflection is 0 at the support. At a fixed support, both the deflection and slope are 0. So now we're looking at two parameters. Okay, boundary conditions. Well, normally this is one of the major consideration when coming up with an analytical solution. Boundary condition is understanding the boundary condition. Now take note for a beam. So I'm just going to put here a simply supported beam. Okay, and let's say that we have a certain loading, say P. All right. So here, this will cause, or this P here will cause a bending of the beam. Can be small, can be large, we don't know. Let's try to put our axis here. So again, we can have this one as 1 and this one as 2. Yep. So somewhere here, there will be a displacement U2. Since we have a transverse loading. So a beam is loaded along its transverse direction. In our conventional axis, it is loaded along the axis too. Now, so of course, we will be looking at two parameters. Now, if I just go back here, one slide back here. So we have now here to consider a slope and deflection. So, if this one is going to bend, there will be a slope. Normally, we define this one as an angle theta. So we have here angle theta, and of course, somewhere here, you have your deflection U2. Right? So we have now two parameters. So theta and that displacement U2. So let's look at the supports. Now, for a simply supported beam, Okay. Since this one is preventing this beam from moving downwards, then of course you know that your displacement along, so let's say that this one is A and this one will be B. So U2 at A will be 0. Yeah? So in order not to confuse you, let's say we have theta as theta 1, 2. So the reason I'm using theta 1, 2 is because this has been used by our lecture notes from Glasgow. So we just have to adopt what they have been using to be familiar. So that's theta 1, 2. Now let's look at your theta 1, 2. So definitely there will be a value here. Okay? So there will be a value there, there will be that slope. So this is not equal to 0. That's for a simply supported beam. Yep. Now at B that will be the same. U2 at B that will also be 0 because this support prevents this point from moving downwards. And of course, since we have a slope there, which will be represented by the symbol theta or angle theta, then your theta 1, 2 at that point B is not 0. Okay, so we're still using the convention that we have, wherein one is your longitudinal axis and 2 will be your transverse axis. Right? So let's have a look. So boundary conditions pertains to the deflections and slopes at the supports of the beam. Okay, that's the definition of boundary conditions. So at a simple support, the deflection is 0. At fixed support, both deflection and slope is 0. So what does it mean? So let's look at a fixed. So when I say fixed, I can also say clamp, right? So many definitions or descriptions in the literature or internet or textbook. So when you see fixed, meaning it can also be clamp. Okay, meaning that you're going to fix one side or both sides. Fixed. So when we mean fixed, say for example here, the assumption for this fixed beam so for this fixed beam, if it's going to deform, it's somehow going to look like this. Sorry, I forgot to put the load. Let's put a load there. If it's going to deform, it's going to look like this, somewhere there. So as you can see at this end, there won't be any slope as compared to your simply supported beam. Okay? So this is an assumption. When you ask why is that so, this is an assumption. That for a fixed beam, it's totally fixed at one side, that there won't be any slope at that end. Okay? There won't be any slope at that end. So, for example, we go back again and say points A and B. So for a fixed beam, so this displacement at A is 0, and your slope at A will also be equal to 0. So that's the assumption for a fixed support. That here we assume that once this one is fixed, both displacement and the slope will be 0. Right? And it's the same here. U2 at B is equal to 0, and then you have your slope at that point B is equal to 0. So these are, so we have already discussed two types of beams. What about the second one? Or the third one? We have a cantilever beam. What is a cantilever beam? Any questions so far? Okay, so these are the assumptions. So we have here boundary conditions, the deflection meaning the U2 or the transverse deformation, and slope and supports. Simply support, the deflection is 0. At fixed support, both the deflection and slope are 0. Okay, each such boundary condition supplies one equation that can be used to evaluate the constants of integration. Just a warning, we will be doing some integration here. Okay, so please prepare. Anyway, that will help you in your second project anyway. So for that, it's really good to at least focus on that integration part of it. I just can't imagine any engineering student who didn't go through differentiation and integration. It's pretty much our training as engineers. So, yep. Yeah, cantilever beam. Now this one is also clamped and free, meaning that one is clamped and the other is free. So let's have a look. Yeah. There we go. Say this one is, let's just put some loading here. Okay? So let's just put some loading there. So what do we have? So if we're going to inspect this one is fixed. Have a look at this one, that is fixed. So that is fixed, and then it's going to deform like that. Okay? So, somewhere along the way, there will be that deflection here, U2. And of course, there will be that slope there, theta 1, 2. Again, let's assign this one to be point A and this one to be point B. So what do we have? Now, it's the same, fixed. Displacement and slope will be 0, but for this one, it is obvious that you will have a displacement and you will have a slope. Okay? Cantilever beam is a clamp free. One is clamped and the other is free. Yeah? So it's going to deform somehow like this. This one here, you will notice that U2 at A will be equal to 0 since it is fixed. And your slope at A is equal to 0. Now, here, just looking at that, there will be a displacement or what we call deflection specific for beam. Your deflection at B will be a value we don't know, so it's not 0. And definitely there will be a non-zero slope. Okay, so basically these are the things that we're going to learn. We have a simply supported beam, we have a fixed beam, and we have a cantilever beam. So pretty much just a combination. If there will be others, it's just a combination of the simply support, the fixed, and the free. So please take note of these boundary conditions. Okay, so just clear yourself from any lectures we had from finite elements so that it won't be confusing. So just consider this one as another subject or another course or another module. Just forget finite element at the moment. Of course, what we have learned so far will also be useful for finite element. Right? So here we go. We have the bending moment equation. So after knowing the boundary conditions, we're going to look at the bending moment, the shear forces, as well as the loads. Okay, so this is how we study beams. We have a loading and there will be deflection. So here, probably we can represent this one as something like this, where we have a load there at the wheels, and then we have forces or reaction forces at the supports. Okay, so this is how a cantilever beam, if we try to analyze it, there will be forces there, and since that is fixed, there will be reaction forces as well as moments. Let's try this one. So, what are we trying to do here? So here we're going to look at shear force diagram and beam moment diagram. Okay? Now for the others, probably you have done this one. Mechatronics, probably not. So let's try to study this one. Probably a review for just for those who took it already. Now let's have this one here, a simply supported beam. We have, say here, a force. I'm looking at 80 kilonewtons, right? Now what we're going to do is, say we have here point A and point B. So let's draw the schematic diagram for this one. So the schematic diagram for this one, so let's try to remove the supports now. Schematic diagram is just a skeletal representation of your structure, wherein you place all the moments and all the loads and all the forces or all the forces from the supports. Okay, so here, if we're going to draw a schematic diagram for this one, it's a simple line, and then we have this 80 kilonewtons, and here, since we have supports here, we have reaction forces. So I'm going to represent here reaction force at A, and then we have here a reaction force at B. Why? Because we know that if we're going to load this one, it's not going to move, and it's going to follow the law of physics, which is the law of static equilibrium. It's not going to move. So if we're going to represent this one with forces, so we have now this force here, and some reaction forces there, so that your structure won't move. Because if you don't have these forces, okay, your structure or your beam is simply going to go down with that force. So if you're going to represent this one, there will always be reaction forces and or reaction moments at the beam or at the supports. So the question is, how do you determine the reaction forces? Now, since we're looking at static equilibrium, probably you're already familiar with the equation summation of forces is equal to 0, summation of moments equal to 0. So these are the conditions you have to satisfy to have a statically equilibrium structure. So, static equilibrium, meaning it's not going to move, okay? Equilibrium. It is constant, it's not going to move. It's like it's at rest, even with the loads being applied. So here, we need to satisfy this one. But, again, always look at your axis. So instead of X and Y, we'll probably just use axis 1 and 2. It doesn't really matter. So here, we have reaction A and reaction B. Now, if you're looking at this one here, so let's try the first condition. Summation of forces, say vertical, is equal to 0. So what do we have? So here, I already assume RA and RB to be going up. Okay, meaning that it's along axis 2, so this one is positive. Nobody's stopping me if I have RA and RB to be going down. So if the sign is negative, then my assumption is wrong. So my assumption here is that RA, reaction A, and RB, reaction B, okay, will be going up, opposite the direction of this 80 kilonewton force. Again, I forgot to put the distance. So let's just say this one is 8 meters. Let's say that this one will be at the middle. There you go. So, summation of force is vertical. RA and RB will be positive since they are at the direction of axis 2. So I have my RA plus RB equal to that force, 80 kilonewtons, or minus 80 kilonewtons. I just move it to the other side. I have now here 80 kilonewtons. I have two unknowns, one equation. I need one more equation, so I have to take the summation of moments about A, or about point A. So summation of moments about, say, A. Summation of moments about A. Now, to satisfy static equilibrium condition, this is equal to 0. So what do we have? So at A, at this point here, moment is equal to the force multiplied by the distance. It is important to have a convention here. Let's just follow the sign convention in this notes here, or in this slide here, wherein we have clockwise to be positive and counterclockwise to be negative. All right. So we have now here 80 kilonewtons. The moment arm is 4, so that will be, and this one will be clockwise. So we have 80 kilonewtons multiplied by that 4 meters moment arm. And then we have this one here, minus that RB reaction force at B multiplied by 8 meters. This will be equal to 0. So why RA not included? Because at RA, your moment arm is 0. RA multiplied by 0. So here, if you're going to look at this one, RB multiplied by 8 meters, this one is 80 kilonewtons, 4 meters. Now take note, you can also cancel out units, really. So here, you have that meters canceling out, and you're left with you're left with a unit of kilonewtons. So sometimes you can always check, you know, that forces will be in newtons, moment will be Newton meter, of course, a distance is in meter. So here, you have now your reaction force at B, that will be 40 kilonewtons. And of course, substituting this RB to this equation, you will now be able to have your reaction force at point A to be also 40 kilonewtons. Now anyway, by inspection, since this one is at the middle, you will know that the forces at the reaction will be the same anyway. And at least this one is just to prove that they are the same. Okay? So take note, the load is at the middle, and you have the same supports. So that means that the forces at the reaction will be the same. So that's how we prove it. RA equal to RB. Okay. Any questions so far? Now, let's look at the load diagram. And what we're going to do here is we're going to place positive forces above this line here. So we're going to attempt, most likely we're going to revise this one. So anything that's positive we put above, anything that's negative we put below. That way that serves as a guide. Anyway, this is just a guide. Whatever you do later, once you're familiar, then you don't have to put in the load diagram. So anyway, this is just an introduction for others. So let's say that anything above this line is positive and anything below is negative. So I have my reaction A, which is 40 kilonewtons, and I have my reaction B, which is the same. And I have my 80 kilonewton load here. I'll just put in the distance just in case we won't be confused. Just in case, so we won't be confused. Oh, 4 meters, thank you. There you go. So 4 meters, 4 meters, located at the center. That's the load diagram, quite very straightforward for a point load, a load acting on our simply supported beam. Very straightforward. So, let's look at our shear force diagram. So our basis for the shear force diagram will be the load diagram. Again, for this line here, anything above will be positive and anything below this line will be negative. Okay? So here, since that is positive, we simply just go up. So we just base this one. Okay? We just base our shear force diagram from this one here. So at this point here, you see this one to be going up. So we go up because it's telling us to go up. So that's our force. So we have a force there, so we're going to go up. And what's the magnitude? The magnitude will be the magnitude of that force, 40 kilonewtons. Now, along the way, we don't have any disturbance. So it will be constant as long as there will be no disturbance. So we can just continue moving. So we have here 80 kilonewtons. We stop here. There's that disturbance over there. And it's going down here. So we probably have to go down. Until when? Until when? So it can be here. It can be here. But because I know the value, so this one will be 40 kilonewtons minus 80. So we have this one to be negative 40 kilonewtons. So we know that it's going to be somewhere here, below that line there, which is the negative value. Okay? So again, along the way, no disturbance, so we just continue moving until we reach this one wherein we have now a force, reaction B, or RB. So since that one is going up, we go up until when we can simply calculate. This one is simply minus 40 kilonewtons, that magnitude here, minus that 40, or sorry, plus 40 kilonewtons, so that will be 0. So why 0? Because we have considered statically equilibrium condition. So your shear force diagram must balance out. It must be 0 at the end. Alright? Shear force diagram. So what's your maximum force here? Your maximum force will be 40 kilonewtons. Okay? If it's negative 50, assuming it's negative 50, then your maximum shear force is that negative 50. Anyway, that sign just means it's in line with your axis 2 or opposite axis 2 or along axis 2. to or opposite to the direction of axis 2. So that's the shear force diagram. So, shear force diagram. Okay? Any questions so far? Moving on. Let's look at the bending moment diagram. So again here, anything that's above this line will be positive, anything below will be negative. So that's the bending moment diagram. For this one, our basis is your load diagram. For your moment diagram, your basis will be this one here. Right? Now this will be a bit confusing as we go on later with more complicated loading. A straight line is a 0th order. So just to give you a bit of introduction, so a line is a 0 order geometry. So let's just put there 0 order. Diagonal line, first order. So 0th order, first order, and we have this curve here. Okay, we simply call this one as second order curve. All right, 0th order, first order, second order. Now, this one is a first order, or sorry, 0th order. So what you're going to expect in your moment diagram will be a first order. So you move by ranking. So from 0, you go to first order, you go to second order, and so on and so forth. So at the moment, we simply have this one as a first order curve, this line here. So for your bending moment diagram, we will be expecting a first order curve. So will it be going there or going down? We don't know yet. We have to base it from this one. So let me just expound on this one. So we have your order, which is 0th order, a simple line. So your first order, that will be either going up or going down. And your second order, going up, going down. Okay? So, if this one is first order, this is going to be second order, and this one is going to be third order. So you increase your order as you move down. Okay? So here, for your shear force diagram, this one will be a first order curve, lines, so not a problem. So we expect a first order curve when we move to the bending moment diagram. All right, what do we have here? Now, what will be the magnitude? The magnitude will be the area of this curve. So what am I saying here? So I start from 0, since this one is first order, and that's positive. Okay. First order positive, or sorry, 0th order positive. So my curve here will be going up. First order positive, I have this one. So I will start from 0, which is this one, going up. Meaning that there are no moments at the support, so I can simply start from 0 going up. And what's my magnitude? My magnitude here will be the area of this one, which is simply equal to that height multiplied by the length, or the force multiplied by that distance. Okay? And this one is simply equal to 40 kilonewtons multiplied by 40 kilonewtons multiplied by 4 meters, so that is now equal to 160 kilonewton meter. All right? So let me increase that. Now, after this one, I have a zero order negative. So if I have a zero order negative, then I move down. Okay? So until when, I don't know yet. So I just move down. So what will be this value? This value must be 160 kilonewton meter minus this area here, which is again 40 kilonewtons multiplied by that 4 meter, so that will be 0. Why is it 0? Because we're following the static equilibrium condition. Okay? So that's your bending moment diagram. And why is this important in the first place? Because we wanted to calculate the stress of the bending, and just to give you an idea, your stress is equal to the moment multiplied by a certain distance y divided by the moment of inertia, or the second moment of area. So we're going to understand this one. So at the moment, before we can calculate the stress, we need M, we need that Y, and we need that I. So we're going to define this one later. So at the moment, we are now successful in determining the moment as well as the shear forces. So this is your maximum moment located at the center. Alright? So what about we have a uniform distributed loading condition for this one. So instead of a point load, we have a uniform distributed condition. Okay. Any questions so far before we move on? Any questions so far? What do you mean? Go down?
Put down. Stress is much more low. 这个旁边连 I 知道吗？如果 I 不是你的这类，打人受对猫的，打落会要命，人家说法。
Okay, have a look at this one. See how you're going to approach this one. Well, anyway, the solution is here, but just have a look. Right, let's do this one before we go for a break. Or probably just have a 10 minutes break. Just have a 10 minutes break before we go solve this problem here. Okay, have a 10 minutes break. So a few things to consider. So may I have your attention now, please. Right, a few things to consider. If we're doing the shear force and the moment diagram, so we go by order. Right? So if this one is a zero order in the load, your shear force will be first order and this one becomes second. So at the moment it's just a simple point load, meaning that we just have 80 kilonewtons there and then we have the reaction forces at the ends. Okay, we go up here, so we're moving from left to right. We're moving from left to right. Why? Because our axis is from left to right. Okay, so we're moving from left to right. Okay? So settle down now. So let me just explain this one. So we're moving from left to right. So the reason why we go up is this one goes up. And we go constant here because there are no disturbance. So we just move along. Okay? Meaning that the effect of that force, 40 kilonewtons, will be constant along the beam until it reaches that point. Okay? So it moves there and then it reaches that point, then it becomes a different value, meaning that this one from here to here goes down. And that's the magnitude. Now, the other thing is this one here. Because this one is a zeroth order, so the next order will be a first order. Why are we going up? Why are we going up? Because this one is positive based on our assumption or based on our convention. Anything that's above is positive, anything that's below is negative. So this one is a positive, so we're expecting to be going up.
Positive and negative is magnitude.
So we expect to go up. And what's the magnitude? The magnitude is the area of this one here. So think of this block. What's the area of the block? The area of the block will be that length multiplied by the height. In our case, the length is 4 meters, and this height here is actually the force, which is 40 kilonewtons. Which is why we go up until when? Until a magnitude equal to this area. So we stop there. So we base it by blocks. Okay? And our starting force, or our starting point is 0 because there are no moment at this point here. So we start at 0. So we start by block. Now, once you have this point here, you move to the next block. So that's the next block. Okay? So why are we going down? Because based on our convention, this is negative. So negative meaning we will be going down here. This is a 0th order, so this one becomes a 1st order. So we go by order. Okay? The lower we go, the higher the order. So in this case, this one is a 0th order, negative. So we go down. Our starting point will be that point there, which is 160 kilonewton. So we go down. We can go down until here, we don't know, but because I already have an initial idea that it's going to end at 0, so I just end it there at 0. But this one can go down there, and maybe somewhere here it goes 0. End of the day, your diagram must end up at 0. Why? Because you use the principle of static equilibrium. Right? So here, this is your starting point, 160 kilonewton. You go down. What will be that value here? That will be 160 kilonewton minus the area of this one here. Alright? And what do I mean by this stress? In mechanics of materials, everything is about forces, deformation, stress, strain. We're just looking into these parameters, so we're making life difficult because we wanted to know what are the values of the stress, what are the values of the strains, what are the values of the forces, what are the values of the deformation. Of course, slope also comes into the picture. That's basically a displacement, which is an angular displacement. That's why it's theta. Now, just to give you an idea, why are we doing this one? Why do we need the moment? We need the moment because we wanted to know the maximum stress. Like I said, here in mechanics, we wanted to know the stress. So how do we know the stress? Just an example that our cross-sectional area, say for the beam, cross-sectional area, just an example. So we have a rectangular cross-section where we have this one to be your B, and that will be your H. Your Y here, assuming that you have your neutral axis, and A meaning neutral axis. Okay, so that line intersecting your centroid. So still, we're going to study a lot of that. So if we have a rectangular cross-section, your Y is actually the maximum distance from the neutral axis to that value, or that maximum value from your neutral axis to the surface. So whether your surface is this one or that, we don't know. But for a rectangular cross-section area, your Y here is 1/2 of that H. And what is I? I will be that BH cubed all over 12. So we're just going to give you the formula at the moment. So if you're going to calculate for the stress, you know the moment, which you have already determined using the beam moment diagram. You know your Y, which is 1/2 of the height of the cross-sectional area, and you know your second moment of area, or the moment of inertia, which is BH cubed all over 12, so you can solve for your stress. Okay, that's our end goal for doing all of these. So we don't end at just determining the moment, we want to know the stress acting on our beam. So that's our end goal. Any questions so far? So knowing that this is our goal, now let's look at the other criteria or other ways of determining a beam moment diagram depending on the load. Right. So here, alright. So this is our problem. We have a beam with uniform distributed loading condition, UDL. So we have a beam with uniform distributed loading condition, UDL. If we're going to look at this one, so we want to know the beam, or we want to determine the beam moment diagram, the shear force and beam moment diagram, and probably to end up determining the stresses or the stress inside the beam, or the maximum stress acting on the beam. Alright, so how do we do this one? Of course, the first step is determining the reaction forces. Now, for this one is quite straightforward. You take the summation of forces equal to 0, and you take the summation of moments equal to 0. Now, in this case, we cannot do that directly. So we need to come up with an equivalent nodal load, or equivalent loading condition. Equivalent load. And how do we determine the equivalent load? We multiply this load density W, so I call it just W equal to 10 kilonewtons per meter. That's the load density. So we multiply this one with the length of the beam, and this must be acting at the center of this UDL. Okay, so let's have a look. So just to calculate for the reaction forces, so that technique is just to determine the reaction forces. So let me have that as RA and RB. This will be point B and that will be point A. Right? So to determine the reaction forces, we must have an equivalent loading condition, an equivalent load. So what do I mean by an equivalent load? So what we're going to do is to have this one as your RA and RB, still no change. But we will have an equivalent load that will be acting at the center of this UDL. So what's the magnitude of that equivalent load? So the magnitude of the equivalent load is equal to that W multiplied by, say that is your length, L. W is, or the small w, is that load density, and L will be the length where you have this UDL. So in this case, you have a UDL across the span of the beam. Okay, so this one now becomes, say, 10 kilonewton per meter. And this is to be multiplied by that 8 meter. We have now 80 kilonewtons. Okay? So, where will it act? That will be acting at the center of the UDL. Fortunately, that length of the UDL, or that UDL acts along the span of the beam. So this one will be acting at the center. 4 meters and 4 meters. So again, we can simply apply the principle of static equilibrium. So that's point A, that's point B. Now take note, this technique is only to determine the reaction force or reaction forces at the supports. When we go determine our shear force and beam moment diagram, we have to use the original UDL. So this technique is just to determine RA and RB. Right, so I just take the summation of moments about A, or about point A. So this will be 0. My assumption here will be that clockwise will be positive and counterclockwise to be negative. That's my sign convention. Okay, so RA multiplied by 0 if you want that. RA multiplied by that moment R, plus we have that W multiplied by that 4 meters, minus you have your RB multiplied by 8 meters, that's equal to 0. So we know W, which is 80 kilonewtons, we will be able to determine your reaction force at B to be 40 kilonewtons. And then take the summation of forces vertical equal to 0. RA plus RB equal to 0. RB is, plus, or minus, RA plus RB minus W equal to 0. We know this one is 80. We know this one as 40. Minus 80 plus 40, that's minus 40, go to the other side. Your reaction A will be also 40 kilonewtons. So quite straightforward. This will be located at the middle, so RA and RB will be the same. Okay, so we have now just RA and RB. questions so far? Moving on. Okay, so we move by order. Now this is how our loading looks like. Let's just try to simplify this one and determine the force diagram or the load diagram. So the load diagram is simple. We just put all the loads going up to be positive and all the loads going down to be negative. So just a guide. So this one is positive, that's negative. So this is our load diagram. So that's our load diagram. We have RA, that will be 40 kilonewtons, and we have RB to be the same, 40 kilonewtons, and we have our UDL to be going down, uniform distributed loading. There you go, and this one will be 10 kilonewton per meter. Now take note, at the load itself, you have a zeroth order. So your shear force diagram will be a first order, and your moment diagram will be the second order. Okay? So let's look at our shear force diagram. We start at this point from left to right because our axis is from left to right, positive, so that's 1 and that's 2. Alright, so I go up first just looking at my 40 kilonewtons. So I start there, 40 kilonewtons. I cannot start using the UDL. I start with that point load 40 kilonewtons. Now take note of this one. Alright? So just take note of this one. Since this one is negative, zeroth order, negative zeroth order, I will definitely have this one. This is zeroth order. The next curve or next order will be a first order based on this one that's negative. So what I'm going to do is to just go down straight. We don't know where we're going to stop. How do we determine that? Well, that's simply this one here, 40 kilonewtons, which is that, minus this area. And what is the area of this one? That is 10 kilonewton per meter multiplied by your distance, which is, I'll just put the distance here, 8 meters. Okay? So that is 40 kilonewton minus that 10 kilonewton per meter multiplied by that distance 8 meters, so that your meter cancels out. That's kilonewton minus a kilonewton. That is now negative 40 kilonewtons. Okay? Now, so we have this one to be negative 40 kilonewtons, and then we have this one here. 40 kilonewtons going up, so we simply go up. And we know that that's negative 40 plus a 40, we know that that will be 0. So that will be negative 40 plus 40, this will be 0. So we stop at 0. So that's one way of checking it. So what is this distance x? Since we want to determine or analyze this one by blocks as we move on, what is that distance x? So take note, this one is 0. Okay, so how do we determine x? So this one is 0, right? So that is 0, that should be equal to that 40 kilonewtons minus that UDL load, 10 kilonewton per meter, multiplied by a certain distance x. We're going to determine x, and x is simply equal to, what do we have? So x is simply equal to 4 meters. Right? So we know it's going to act in the middle anyway. But anyway, this one is one way of checking that what you're doing is correct. But anyway, we're going to need that x because we need this area later on. Take note, we're still at shear force diagram. We need a deep moment diagram. And this one is already a second order. Anything that's above, positive. Anything that's below, negative. Whatever shape you have, or it can be going down there or going down there, it's still positive and that's negative. So let's have their positive and negative. Okay? Alright, so again, we base our beam moment diagram on the area as well as the curve. So this one is a first order, so what's going to happen is we're going to have a second order here. And since that one is positive, right, since that one is positive, then this one is positive, there, it's positive. Okay? You base it from above. That is positive, and that is a first order, so positive, so you go up. So I go up, and what is my magnitude here? My magnitude here will be this area here, area of a triangle. And what is the area of a triangle? My moment here will be 1/2 multiplied by the base, which is 4 meters, multiplied by the height, which is 40 kilonewtons. So that is 1/2, that's the area here, 1/2 multiplied by, say, the base, which we already determined as 4 meters, multiplied by the height, which is 40 kilonewtons. So we have now this one to be 80 kilonewton meter. So that's the unit for the moment. So again, we study by blocks, right? So we just study by blocks. So we have now this one here, that's positive, we go up. First order, so this one must be a second order, that is positive, so we go up. Second block is this one here, that is negative, that is first order. So we should have A, second order, negative, so this one goes there. And what is this magnitude? This magnitude will be from the starting point, which is 80 kilonewton meter, minus the area here, okay? That will be minus 1/2 multiplied by that base, which is 4 meters, multiplied by that height, which is 40 kilonewtons. So this one becomes 0. There you go. So your maximum moment will be this one here. And you should end at 0. Why? Because we're actually satisfying the condition for static equilibrium condition. Summation of forces equal to 0. Summation of moments equal to 0. Alright, so just looking at this one, we have now this UDL. Those are your reactions. First order shear force diagram, and this will be your bending moment diagram. We'll have a lot of exercises on this one. These are still the basic ones, as you can see. In mechanics, everything is about forces, displacements, stress, and strains. So please take note of that. So once you have the moments, or once you have the loads, then the next step is actually determining the stress acting on your beam. Questions so far? Okay, so just a review. Now anyway, this is, well, this one is very standard. If you have this type of loading, normally this is how your shear force and beam moment diagram will look like. So take note, in your shear force diagram, you have a first order, or sorry, 0 order. So your beam moment diagram will be the first order. So that's positive, so you should be going up, and that's negative, so you should be going down. Okay, so which is what we have here. Next one, of course, if you have a UDL. Now take note of this one. Our boundary condition is simply supported. We don't have a moment at the ends here. If you have simply supported, we don't have any moments at this end here. For a fix you will have, but for a simply supported, you won't have. And we're going to have that example. So what we did here was, knowing that we have a support here, there won't be any reaction moments. For a simply supported beam, there won't be any reaction moments. There will only be a reaction force. So what do we mean by reaction force? It's going to counter the force acting on the beam so that it will satisfy static equilibrium condition. Because without the reaction forces, if we apply a load to the beam without any reaction forces, it's just going to go down. So it doesn't satisfy the realistic condition. So we have to apply reaction forces so that if you're going to put in something here, then that reaction forces is going to counter that movement, and it's going to be a static equilibrium condition for the case of the beam. Now, so this is what we had. So we have the reaction forces. We can use the summation of forces vertical equal to 0, summation of moments about a certain point. Of course, I'm just using about A. You can also use about B if you want to determine the reaction forces at the supports. Next step is to draw the shear force diagram. I would advise to have the load diagram for those who are still struggling to understand. Do the shear force diagram, or sorry, the load diagram will the forces going up will be above this line, and the forces going down will be below this line here. So you have a positive and negative, which you will use to guide you in determining the shear force diagram and the beam moment diagram. Okay, so we study by block. The magnitude of this one will be based on the area above. Okay, so the magnitude of this one will be based on the area above. Of course, starting with this point here. So we move by order. So as we go down, load diagram, shear force diagram, beam moment diagram, the order increases. The order increases. So this is what we have here. To be able to get the reaction forces. So since this one is a UDL, for the purpose of getting the reaction forces, we need to have an equivalent load. And how did we determine the equivalent load? So we determine the equivalent load. That's simply the load density multiplied by the length where that UDL is acting. So we took that equivalent load and we determined the reaction forces. Okay, just an example here. So let's say that's a distance d, and that's w. Your equivalent load will be w multiplied by d. Okay? And this one will be acting at a distance from here, that will be d all over 2. Okay? Any questions so far before we move to the next one? Cantilever beam. So we're looking at simple conditions. Boundary conditions, we just have simply supported, we have free, we have fixed. So these are assumptions for our boundary conditions. So let's look at something that is fixed at one end and that is free. How about that? Okay, what do we have here? We have one to be fixed and the other to be free. So here, you will have a reaction force. And definitely you'll get a reaction moment. Why? Because you have a fixed support. We didn't have that for a simply supported support or boundary condition. We don't have the moment. We only have reaction force. But for a fixed boundary, which is represented as this one here. For a fixed boundary, we have a reaction force and a reaction moment. Let's try to prove that. Why do we have a reaction moment? Or what will be the magnitude of the reaction moment? Let's apply the rules for the static equilibrium condition. We have the summation of forces vertical equal to 0. So we have RA positive simply equal to 80 kilonewtons. That's straightforward. Summation of moments about A is equal to 0. We look at our convention again, clockwise to be positive, counterclockwise to be negative. So we have, initially we assume this one to be counterclockwise. Okay, so counterclockwise. So we have this one to be clockwise, positive. Let's just start with the positive first. So we have here 80 kilonewtons multiplied by 8 meters minus this one here, MA, which is our reaction moment. This is equal to 0. So our moment at A, or reaction moment at A, will be negative 160 kilonewton meter. So we're going to use that sign convention in our shear force and bending moment diagram. 640. I just added that. What happened there? I'm confused. Okay. Like I said, we're going to use that sign convention there. We're going to use whatever sign convention. If we have this one to be positive and negative, we're going to use that sign convention in drawing our shear force diagram. Okay? Let's look at the load diagram. Let's start first with the load diagram. If you're starting, you start with the load diagram first. Now we have a moment. Now this one only appears at the, if we determine our bending moment diagram. So it won't appear in the shear force diagram. So for your shear force diagram, what appears will only be the effects of your forces. Right? There you go. Shear force diagram. That's simply positive there and negative there. Okay. What happens now? Now, for your shear force diagram, you just have your forces to be affecting your shear force diagram. Okay? So let's have a look. RA is positive going up. So that will be 80 kilonewtons. No disturbance, so I just continue moving forward. And then I stop here. I go down up to which value? So this one will be 80 kilonewtons minus 80 kilonewtons equal to 0. So I know I stop at 0. So this is now my shear force diagram. Stay straightforward here. Very simple. I end at 0. Why? Of course, I satisfy the condition for static equilibrium. I always end up at 0 because I determine my reaction forces based on static equilibrium condition. Now what about the beam moment diagram? That's positive, that's negative. This one is 0 order, positive. So we have your 0th order. Okay? And you have your 2nd order, positive, negative. Okay. Now the thing here is we have a negative moment. The thing here is we have a negative moment. So if we look at your beam moment diagram, we have a negative moment. So we go down. We have a negative moment because we have MA there to be negative 640 kilonewton meter. So this one now is negative 640 kilonewton meter, which is based on this one. So that we have to go down. Next, we have this positive 0th order, positive 0th order, so we go up. Until when, we don't know. So let's just add this one here. We start at negative 640 kilonewton meter, and then we add this area here, which is the length, multiplied by the height. What is the length? That is 8 meters. What is the height? That will be 80 kilonewton. So now I'm correct. 8 times 80 is 640. So we have now this one to be 0. Again, it's 0. Why? Because we satisfy the condition for static equilibrium. One way of checking your answer. So your maximum moment will be this one here. 640 kilonewton meter. So take note, if you have a convention here, you have to maintain it all throughout. Okay? So we have already a convention here, so we have to maintain it all throughout your shear force and beam moment diagram. Okay?
Oh, this that's a negative 6.
Okay, you have a UDL. So next one. You have a UDL and you have a cantilever beam. So you just use the equivalent load assumption to be able to calculate for the reaction force and the reaction moment. When you draw the shear force diagram, knowing that this one is a zero order, this will be a first order. For your beam moment diagram, since this one is a first order positive, that goes down there, and then this one goes up, but this one is a second order curve. This one is in Moodle, so you can simply download it if you don't have it yet. It has been there. Okay, it has been there since. So with that, you can actually look at other loads and so on and so forth. So here you go, load diagram, shear force diagram, moment. Load diagram, shear force, moment. load diagram, shear force, moment. Okay, so you have all of these in Moodle. These are the moment of areas or second moment of areas. This is the centroid. I'm just telling you what to expect. And there you go. This will be your project assignment 2. Sorry, project assignment 2. So you have to do this one plus the finite elements contribution analysis. Okay. Anyway, we will be going through a lot of these examples as we go on. So at the moment, just try to absorb what you have learned so far. Sorry, we're going to also have some exercises, so you will be able to assess what you have learned at the moment. So don't worry about that. You will always have. Sorry, please. Because I don't want you asking the things that I have been saying. I mean, it happens a lot of times, so I have to stop you first and listen to what I say. Now, we will be having exercises again so that you will be able to gauge yourself. Okay? Do let me know what you want to learn from this one. Just go read, and maybe if you have some input, just let me know, and I'll try to incorporate that in the exercises that we're going to do. So please help me help you. Read through this one, tell me what's not clear, I'll try to discuss. If that's not enough, I'm going to put that in the exercises so you can apply what you have learned and gauge where you are at the moment. Okay? So do let me know. Any questions so far? So just a review, just give me a few minutes to review. Take note that we have here boundary conditions. It's important to learn boundary conditions because at the moment we're still at analytical solutions. Once we go to finite element, boundary conditions again will be another problem. So it's really important to spend some time learning the different boundary conditions. For beams, we're just looking at simply supported, fixed, and free. That's all. Simply supported, fixed, free. These are the boundary conditions that you should know. So here, in mechanics, we just wanted the stresses, the strains, the forces, and displacement. Of course, moments comes into the forces and so on. So we had this one here. We have the load diagram, shear force diagram at the moment for this simple loading condition. We have the UDL, so try to learn how to get, the problem here is trying to get the equivalent loading condition, which is quite simple already. And then of course look at the fixed end, quite complicated or quite confusing for a start. And finally, a combination of UDL and a cantilever. So please have a look and we'll have more exercises as we go on. If there are questions, just send me an email. If not, then you're dismissed. I'll see you tomorrow. Thank you very much.